So hello everybody. First of all, I would like to thank Mr. Ahmed Jeraya and Salvador Mir for inviting me to this conference and allowing me to present my talk. I would like also to thank Michel Zakharovich, who decided to come and make some introduction. And also, I would like to thank very much all my friends and colleagues. Some of them are here, Christian Bernard, François Bertrand, who helped me to refresh my memory when I was preparing this conference, and they gave me many interesting details which I could have forgotten. So in my conference, I will present the story of Ball's CPU integrated processors. And I will talk about the contribution of Professor François Anceau to this story. So my talk is dedicated to honor the memory of Professor François Anceau. We all here know his merits, and among many positions he held, I remember that he was a teacher at the INPG. Of course, he was my teacher, and he was the director of many theses, and he was also the director of computer architecture laboratory. And but of course, some people who are here and who will talk, they know some other parts of the story, so they will say more about his other activities. As you know, at the beginning of 70s, first microprocessors were released, and this was fascinating many engineers, and especially also François Anceau. And he was able to induce this fascination among his students and collaborators. So I will talk about the history of Ball processors, but before that, I will make some introduction about Ball. Because maybe some of them don't know the exact story of Compagnie des Machines Bull. So I will talk about how Bull was founded, history of Bull and different activities, a little bit about systems, then about projects related to VLSI CPUs, contribution of Professor François Anceau, and also I will tell some words about CAD tools developed at Bull, design methodologies which were used, and verification and hardware tests of these circuits. Okay, so the history of Bull. Bull is the name of a Norwegian engineer who was working for an insurance company, Storebrand. And in 1919, he filed a patent for ordering, recording, and adding machine, which was called tabulator, and which was using punch cards. Unfortunately, he died quite young, but he had good friends and collaborators. And one of his friends, Andreas Knudsen, Kurt Andreas Knudsen, promised to him to continue the work on this new concept and new machine. And so in 1930, there was a company which was founded, which was called Bull, by Andreas Knudsen and some collaborators, and Belgian Émile Genon and Swiss men which joined them in 31, which was called Hans Egli. Yes, and so this company was transferred to Paris because this is maybe a little bit astonishing, but at that time, economic laws were better in France than in Switzerland. So, okay, so here you have some interesting dates in the life of Bull Company. Between 33 and 90, the name of the company was Compagnie de Machines Bull. And were some other important moments in history of Bull was the merge with CDZ, the nationalization in 82 when Mitterrand came to power. Then there was more than 10 years later, a progressive privatization. And in 2004, Bull became again a private company. In 2010, it integrated Amesis, and in 2014, it was bought by Atos. On this slide, you can see the kind of genealogy tree of Bull. It is quite complicated. Well, of course, I will not explain all the details. You can see the names of different companies which were collaborating with Bull, or which were having a common project, or which were bought by Bull, or who bought Bull. So it was a quite complicated story. So Bull was an IT company which had many activities, not only constructing computers, but also developing software and developing different other inventions, like the card CP8, and well, globule maybe does not work very much. You can see, yes, I have a pointer here. Gamma 60, which was one of the most modern computer at these times. And so here you have some dates for these inventions and products. The most important, of course, I will not read all of this, but most important was Gamma 60 commercialized in 1958, invention of tab micropackaging in 73, inventions of CPU card, which was co-invented, well, rather invented by Michel Hugon, what told me my colleagues from Bull. And Roland Moreno did not really play a very good role in this story, but you can find the explanation on the internet. Well, for example, creation of Ada language, and the name of informatique also was used by a person, Philippe Dreyfus, a director of Bull Computing Center. Donc in the 21st century, Bull focused his efforts on developing supercomputers or high-power computers. And so I was working at Bull at this time. The most important dates for me was Terra 10 in 2006, which was #1, classified by top 500 organization, #1 in Europe, and #5 in world. And it has it achieved 55 teraflops with 30 terabytes of RAM. Then in 2010 there was Terra 100, which was of course even more performant. And in 2016-18 Terra teramil supercomputer, which achieved 25 petaflops. So I will talk now about the Ball Systems project and VLSI CPUs. So maybe some subject which I talk about, maybe they are obvious for you, but maybe not. So I will tell some things which may be obvious for you. Bool's proprietary system means mainframe systems. Bool had mainly two lines, one which was called DPS7, with system G cos 7, and which was created in 1962 in France. And the other line, which was developed in the United States, which is called DPS8. And so these systems are much more complicated than just a microprocessor or just a PC. They manage processors and segmentation, use different mechanisms to allow transactional systems to work, and they have microprogrammed firmware. So the decision to create an integrated CPU for these systems was quite revolutionary at this time. This is just an illustration about how complicated a mainframe system can be. It contained not only the processor, but also the central execution processor, but also service processor, input-output devices, different microprogram systems and application. So, of course, I will not talk about all this. I will talk only about the CPU, so Central Processing Unit, which was implemented, which is implemented in different techniques in function of technologies which were available at this time. So why integrated CPU processors? The technological progress was fascinating French engineers and all engineers all over the world. That was the idea of François Anceau and Michel Zakharovich to ask Ball to implement a CPU of Boole DPS7 system in an integrated VLSI processor. Yes, so I recall this idea. So the first idea was to design one integrated VLSI processor to implement the whole CPU of Boole mainframe computer for the PS7 line. You will see in my presentation that it was not so obvious to realize in the 80s. But anyway, so Michel Zakharovich asked Christian, collaborated with Christian Joly, and they decided to create the Altair project, which started in 1984. And François Anceau moved from Grenoble to Leclé-sous-Bois, and he invited several people from Grenoble, from his team, to work with him. I've put on this slide some pictures available. Shuki Yankee also is here. So from left to right is Christian Bernard, who is here. You will have the possibility to ask him some questions if you want more details. Samuel Shuki Yankee, who also I have seen him. Yes, he's there. Christophe Materon, where you are, we're there. Aziz, well, Wardani, he's not here. And and I don't think he's connected. But he was informed about this conference, and François Bertrand also, who came. I don't have his picture. I will add it to the next version of his presentation. And there was also Jean-Pierre Schelkopf, and unfortunately, it's well, it's impossible to contact him, so I don't have his picture, and me, and maybe some other people. What I wanted to add also is that my presentation is based off what I remember and what I lived. So maybe I forget some people, or maybe I forget some facts. So you are allowed to correct me or to complete this information. And I will be very thankful to you if you add some more pictures, some more information. Altair team was also staffed with some people from Bol. I don't remember all the names, and I don't have all the pictures, but there was Philippe Odo and Jean-Claude Cassonnet. I am in contact with them, so I could get the pictures. Josiane Carivel, Marie-Odile Lamarche, who were working in microprogramming. And also the same remark, if some of people participating to this conference have some more details about people from Bol working on this project, I will be thankful. Okay, so Altair project was the first attempt to implement DPS7 CPU in a single VLSI circuit. And also the idea was to use a custom design. We managed to realize a test circuit, which I will show you in the next slide. So this is the test circuit, which in the middle you can see the data path, which was, I think, programmed by Lubric, no? Christian Bernard, you can confirm. And some other chips, test chips, which was not specially related to DPS7. So this circuit was realized in 1985. But in 1986, the management decided to stop the project. And of course, it was a big shock for some of us, maybe not all, but some of us, especially for François Anceau and for me also. And the reasons was underestimation of the complexity of the DPS7, almost not existing CAD tools to develop the circuit. And we didn't have much experience, and we didn't, the team who came from Grenoble didn't have the knowledge of the DPS7 architecture. So the project was delaying each month. And finally, Christian Joly decided to stop it. I remember very well this day. However, we considered that it was a very enriching experience and was beneficiary to the future project in Bol. Now I will talk a little bit about Ares project, which was led in parallel with Altair, because this project also had an influence on the next project after that. What can be stated is that it was, in fact, it was managed and it was ongoing during the same period from 83 to 86. And the people from this project say that it was the first DPS7 implemented with VLSI chips, but with many VLSI chips. And so it was not a single, the CPU was not a single chip. And also they used the standard cell technology. So it was not designed with custom design. This is the difference between the idea of Altair project and Ares. But ARES was a very successful project. Here you can have a look on the architecture of the processor. There were 6 VLSI implemented for the CPU, but which were housed on one single board. The previous version of DPS-7 system, they needed 112 boards for the machine, so it's a very, very big difference. Previous versions were realized with TTL technology. And for cache, there was 4 VLSI. Here you can see the one of these chips which hosted. So there was 1 million of transistors in 14 different chips, and with CMOS technology working at 6.6 megahertz. And for memory, I put here the names of managers for this project. You have the names from left to right. In the middle, you can see Christian Joly. Here, he is here, Christian Joly. And here on the right is Dan Humblot. For systems, complex systems like DPS-7, what is very important is the day they call GCOS ready. It means that everything was put together, the machine was constructed, and the system is running. Okay, so in '86, both projects were finished. Altair was stopped, and ARES was finished. And the management of Bull decided to launch a new project called Auriga, which goal was still to implement, realize, design the DPS-7 CPU, but using custom design methodologies. Here on this picture, you can see the managers, Michel Guillemet, Jean-Jacques Perrault, Philippe Vallet, Hubert Franzetti, Jean-Louis Fressineau, and Alain Grener. And so this project was a success. We had 5 million of transistors located in several chips. There were 5 chips for CPU, so you can imagine the complexity of the processor that needed 5 chips to be implemented. I was personally working on EAD chip. And here you can see the standard cell chips which were used for memory control. Okay, so here you can see the pictures of 2 teams, the EAD team, where with Philippe Vallet and me here, Christian Bernard, Laurent Ducousseau, Gérard Humeau. I forget the name of this lady. Oui. Okay, and here the FPP team. Some people told me that there are similar pictures for other teams, but I didn't find them. So if you know somebody who has these pictures, I will be grateful. And so after Auriga, which was called afterwards Auriga 1, the management decided to launch Auriga 2 project, which the goal of which was to effectively implement the CPU, DPS-7 CPU in one chip. So we had somehow different chips of Auriga 1 put into one chip. You know, on this picture you see the layout of Auriga 2 and the chips which are arriving. Of course, in such kind of work, you need to what's going on? you need to rework the elements and the connections between these chips. So it was in 1994. It was the realization of François Anceau's dream to realize. It was realized almost 10 years after what he was proposing. And so here is the Origa 2 chip, which was hosting almost 5 million of transistors in a single chip. After that, there was another Origa 2, well, Artemis 2 was a redesign of Origa 2 in 96. And then I can show you some pictures of the team. Probably the people who were participating will recognize some of their colleagues. Okay, so this is the end of the story of Origa 2. But I would like to talk also about DPS-8 projects, which were held in parallel, more or less in parallel, between 1989 and 2004 in United States. Why? Because in fact, there was a designing center also in Phoenix, in Arizona. They were developing DPS-8 system, and so the French management decided to export French know-how to the United States, which is also a quite original idea, because normally people think that everything is come from United States to Europe, but here we had our know-how, which was exported to United States. And I was participating in some of this project. There were also a little bit parallel. RPM2 was like Origa 1, Jupiter 1, and like Origa 2, and Olympus like Artemis. And so there were French team who was sent to Phoenix on RPM2. Their names are here: Boyer Chamard, Michel Do, Jean-Baptiste Ducatez, Didier Marcon, moi-même, Manuel Ortiz, and Bruno Pissembono. Unfortunately, I don't have all of the pictures for all of them. The managers was Rose Gunter and Lowell Macaulay. I am still in contact with them. And here you can see the working dinner in Phoenix. This is a very typical working dinner, because we have a red wine. And here at the left is Michel Do. Here Michel Guillemet, Jean-Baptiste Ducatez. Only the back of Michel Sakharovich and me. I don't remember who took this picture. Okay, so I don't have a photo for RPM2, but Jupiter 2, you can see it's quite dense, 7 million transistors. Then it is the layout of Jupiter 2. A kind of similar main blocks, AX for address calculation, FP for floating points, DN for decimal calculation, KC for cache, and DT for cache RAM. The next one was Olympus, 26 millions of transistors, mainly of course due to RAM. And then Olympus 2, well, this is the picture of the plot, not on the circuit, because many levels of metal didn't allow to really see how the circuit is inside. Okay, so you can see that Bull was a modern company which were following the technological progress. And I prepared this diagram or curve because very often Europeans have some complex against the Americans. So I asked myself, if we put on the line the density of Motorola and Intel processors, how Bull circuits can be compared to them. So in white point you have Bull circuits with the corresponding date, and in green Intel, and in red Motorola. And in fact, you can see that Bull had the same technologies and same advance. At the very beginning, I was surprised by this curve, but in fact, it's not surprising because we were using the same, the most modern technologies available at the time. Okay, so this is the end of the part of my presentation concerning the CPUs and the hardware designing. And this slide comes from Alain Guyot, who is present here. It is just to show well, the progress which would be made on cars if they were following the same curve of progress as integrated circuits. So if during 45 years cars would progress in the same way, the speed should be 3,000 kilometers per second, consumption 1 liter per 100,000 kilometers, etc., etc. You can read all of these numbers. It is quite astonishing. Okay, so to end my presentation, I will talk quickly about computer-aided design at Bull, because it was a very important part of work. Well, I was personally focused on the designing, so this was fascinating for me. But behind the designers, there was a very large team of people who are developing CAD tools, which were very performant and very modern, and probably some of them could have been commercialized by Bull, but it was not done for marketing reason and cost reason. This is just a list to show you how many CAD tools were developed, and I will give you some examples. For example, for design. You know, the design is composed of several stages: functional design, logical design, and physical design. Functional design, it's mainly human activity. I mean, you start from the set of instructions, plus you have a document for Bull, what it was called PA800, which describes the execution of each instruction, what it is doing, what is the timing, and the register. So this allows you to define the functional blocks of the machine. And then logical design consists of describing in a LDS language. There existed at Bull LDS, logical description language, which allows you to describe all the functionality of the machine. And this language will be translated into gates, logical gates. So for regular blocks, you had the tools which allows you to construct the data path or ROMs and RAMs in a regular way. So there was a tool called ASR or GenLib who did this for what is called irregular blocks or control blocks in general. I wanted this too. I don't know why. Well, yes, this is my animation effect. It comes. Okay, so it is much less regular than data path. And these cells are placed by tools which were developed, which was called the bonsai. And ChipComp, I think it was quite a rather commercial tool. And then there was a tool developed also, which was called the Kiops, which allows to route the connection between different blocks. And at the end of the VLSI design, you obtain a description of mask, which is called a PG tape, which is sent to the founder. And in parallel with the design, there is a verification, which is applied at each stage of the design. This is a little bit upside down. You have functional verification, which starts very quickly on what is called a reference model. A reference model is a model written by the designers. Then you have logical verification, which is run on an extracted model, and physical verification, which is run on the description of the circuit masks. And here again, you have the list of tools developed by whole CAD team, which were used to do some kind of, this is for physical verification. DAX, Desafin, Grog was a quite modern tools, allowing to recognize from the masks of the circuit to come back to the transistors, then to come to gates and extract the equations. So it was a very modern and unique approach at this period. There was in logical verification, we were using formal proof, which allowed to compare real design with the specifications. And then, of course, there were a lot of simulation which were run with different simulator. We had automatic test generated with Tagger. We had verifier to verify the results of the test. So you can hear, well, it's a kind, pardon. It's a picture showing how from logical model, so the equation written by hand, we obtain the description of the circuit, so the description of the mask. Then you obtain extracted model, and this model can be compared, and you can run different kind of verification on this two models. And also there is a stage called hardware tests. Hardware test is, these are the tests which are run on the real circuit and which are using a scan path. Scan path allow you to force into the real chip the patterns that you want, and then execute step by step and obtain the results which are automatically compared to what you are expecting. So you see here 6 tools which were developed in a CATI suite, was called CATI suite, to test different parts of the circuits. Okay, so well, it's very in very short time. I wanted just to stress that the designing on the VLSI needs a lot of verification and tests at different stages of the development. And here you have a kind of diagram showing you the complexity. I probably, I don't know how to, yes. Well, this is just to show you the complexity of the whole environment which were developed. This is, on this slide you have the functional design, logical design, physical design, and then it goes down. Logical design for physical layout, and from the layout you have physical extraction, and then you go up with all the verifications, and here you obtain an extracted model which is used in functional verification and which is compared to hardware structural model. Okay, here is a little bit the same, but in more concise way. Okay, so that's it. You can see here some pictures of some circuits. This is EAD from Origa 1, Jupiter 2, another circuit on which I was working for Origa 2, and IOD circuit for Origa 1. And so during 20 years, Bull was developing integrated processors for its systems and machine. And this was a very nice period for people who like the design, because we were doing we were discovering and inventing a lot of things, and we had the impression of participating in the conquest somehow of a new world. And also the people from CAD team was also developing very original tools. And we were greatly appreciating the collaboration between the design team and the CAD team, because these people were close. So when during the design we were discovering some problems with the tool, we could talk with a colleague, tell them, and they were correcting the problems. And after 2004, Bull stopped developing the VLSI, so Bull started to use commercial tools, and so we could notice the difference of the collaboration. It was much more difficult when there were some problems with commercial tools. We had to write a special message. It had to go up in the hierarchy, down the hierarchy. So often we were receiving the response 1 month or 2 months later. So it was not as nice as with collaborating with people who were working at the same place than we. So at the beginning of 20th century, of 21, I don't, I'm not sure. Well, at some moment in history, Bull management decided to stop the development of dedicated VLSI processors for DPS-7 or DPS-8 because they considered that it was costing too much. And in meantime, the commercial processors became powerful enough to allow the execution of DPS-7 and DPS-8 systems using, of course, the software engineers had to rewrite the system to put on these commercial microprocessors. And so they decided to use Intel processors. So as a conclusion, I can say that Bull was an European, multinational, and innovative company. It was the only European manufacturer of high-performance proprietary mainframe systems. And it is a strategic issue for Europe. Bull had talented and competent and dedicated engineers. And well, I am not sure if Bull is still existing because Ahmed is saying that it is existing, but at Athos. Ball was bought by Athos in 2014. They are saying us that Athos took bull and digested it, and it does not exist anymore. So I don't know. So anyway, if we are still in 2031, we may be able to to celebrate the 100th birthday of bull. Okay, so I would like to finish with many thanks to Professor Anso, François Anso, because he inspired us to walk on a new path. So it is almost the last slide. But, well, just for history and memory, there was a book edited by people from Ares, very interesting, about how a computer is designed. And so here I thanks also to many people who helped me to prepare this presentation, and also the references. And at the end, this is a gift, my gift for you. This is a picture of a plot, EAD plot, at La Villette, Musée de La Villette. It is me with my nephews. And I found this in '94, visiting La Villette, and I was very surprised because I didn't know the plot of my chip was at La Villette. Well, unfortunately, it's not there anymore. Thank you very much for your attention.
Merci. Donc, forcément, une certaine émotion à la fois de parler de François Anso, puis d'être là dans un amphi que j'ai connu il y a 55 ans, en arrivant ici, puis de voir des têtes connues à l'époque. Donc oui, je vais parler d'un moment assez particulier dans la carrière de François, qui est sa thèse d'État. Particulier parce que ça contraste beaucoup finalement avec le reste de ses activités. Donc ça a déjà été évoqué, sa manière de tout voir à travers la hiérarchie. Et donc, voilà, on fait comment? Comme ça. Voilà. Donc, bon, on la trouve sur Internet, hein, sa thèse d'État, thèse François Anso, vous trouvez ça. Et donc, soutenue en 74 avec comme président Kunzmann, Arsac, Bollier, Krakowiak qui est dans la salle, et puis Gabriel Saussier qui a été cité aussi comme une des colocataires du couloir de la mort, je dirais, entre avec le troisième larron Mermet. Voilà, ce qu'on peut dire, ce qui est intéressant, c'est que la thèse d'État de François Anso, c'est le couronnement de sa carrière, disons, universitaire, hein, qui a commencé, c'est un couronnement assez bizarre, puisque vous savez que François Anso n'avait pas son baccalauréat, et qu'il n'était pas admis en 6e, hein, parce qu'il faisait trop de fautes d'orthographe. C'est Paul Anso qui m'a rappelé ça il y a quelques jours. Et à chaque fois, il a réussi à passer d'un cursus où il était à un cursus dans lequel il n'aurait pas dû être. Parce qu'à chaque fois qu'il était quelque part, il était le premier, il écrasait tout le monde, il y avait toujours quelqu'un pour dire ce gars-là, il ne peut pas rester là, il faut qu'il aille plus loin. Et d'étape en étape que je ne détaillerai pas, il s'est trouvé N fois par exception à passer au grade suivant. Et en particulier, donc, il s'est retrouvé à devoir passer le summum, hein, la thèse d'État, qui est une notion assez compliquée à expliquer à nos collègues anglo-saxons. Mais à l'époque, c'était pas rien. Et bon, bah là, il s'est arrêté parce qu'après thèse d'État, il n'y avait plus rien. Hein. Et donc, c'est très différent de son travail. On l'a tous connu comme un bricoleur de génie, jamais plus content que s'il avait une télétype ou un moteur d'avion à réparer. Et puis après, les chips, le reverse engineering. Il adorait faire du reverse engineering. Et sa thèse d'État, on peut dire, c'est le contraire un peu du reverse engineering. Alors moi, j'ai bien connu cette époque de thèse parce que j'ai dû être un des premiers, sinon le premier chercheur embauché par François en 72. Et en plus, j'ai travaillé sur son sujet de thèse d'État, en ce sens que j'étais chargé de faire un simulateur, de faire un langage opérationnel à partir de ces idées. Un outil de simulation de systèmes hiérarchisés. Alors, les idées principales, c'est que... alors, également, une chose qu'il faut dire, c'est que pour passer une thèse d'État, il fallait quand même faire quelque chose d'assez abstrait. Hein. Donc, forcément un peu différent de ce qu'il faisait avant. Il avait travaillé avec Merlet sur Cassandre, tout ça, qui était d'implémentation assez dure. Et donc, il avait Kunzmann comme président de jury, donc il ne fallait pas faire du bricolage pour avoir une thèse d'État. Et donc, il s'est dit, je vais faire des choses abstraites, enfin, je caricature un peu. Et son idée, mais qui coïncidait quand même avec ses idées profondes sur les systèmes, c'était un système, c'est une hiérarchie, un système est une hiérarchie de niveaux. Alors l'originalité, quand il disait ça, c'est qu'il voyait ça aussi bien au niveau des plus hautes applications des langages de très haut niveau, comme Lisp, etc., jusqu'au niveau de la bascule. Donc il voulait trouver un formalisme qui permette d'exprimer de manière unifiée ces différentes choses. Et alors il a introduit des vocabulaires, des concepts assez particuliers, assez originaux, comme la notion d'association, de dissociation, d'articulation. C'est très abstrait, sa thèse, en fait. Et puis, également, des êtres, donc des êtres synchronisables, des êtres inanimés, objets inanimés, etc. Et ce qu'il faut dire, et avec tout ça, le but c'était de décrire un peu toutes les connaissances informatiques en architecture depuis le très bas niveau jusqu'au très haut. Et par exemple là-dedans, il formalisait des choses comme les fameux sémaphores de synchronisation de Dijkstra, les P et les V, qui étaient quand même, je dirais, pas très... Les gens ne faisaient pas trop de philosophie à l'époque, c'est-à-dire on implémentait, tous les Américains, on implémentait les OS, etc. Et lui a voulu mettre une espèce de couche philosophique unifiée sur tous les niveaux. Bon. Avec une grande focalisation finalement sur l'aspect description des choses plus que l'aspect computation, exécution. Et tout ça, évidemment, avec Jean Kunzmann comme patron de thèse, il baignait un peu dans la théorie des réseaux de Kunzmann, théorie des graphes, on verra à travers de certains schémas. Alors, sa thèse, en fait, a été découpée en 3 parties. D'abord, sa théorie. Donc, on va voir des dessins tout à l'heure. Ensuite, l'application de sa théorie à l'état de l'art. Donc, là, il reprenait tous les grands concepts d'architecture, aussi bien logiciel que matériel, des OS, etc. Et puis, point par point, les mémoires virtuelles, les machines virtuelles, toute la virtualisation, parce que tout ça existait. Tout le cloud d'aujourd'hui existait évidemment à la fin des années 60. Les pipelines, les bus, les processeurs entrée-sortie, il prenait les choses une par une, puis il montrait que la théorie qu'il avait appliquée, qu'il avait énoncée dans son première partie, marchait bien pour ces choses-là. Et l'allocation de processeurs, et ainsi de suite. Et puis la troisième partie, et là c'était un peu différent, il avait eu un contrat pour concevoir, c'était je pense quelque chose qui lui a plu beaucoup, pour concevoir un ordinateur à partir de rien. Donc c'était un contrat avec l'Institut français du pétrole pour concevoir une machine qui devait être une petite machine qui puisse s'emporter sur le terrain et qui soit adaptée aux calculs scientifiques nécessaires à l'industrie pétrolière. Donc, ça s'appelait géoprocesseur. Alain Guyot, tu as travaillé sur le géoprocesseur? Non, mais c'était donc début des années 70, je pense 72, 73, je pense. Et donc, on verra un peu. Donc, c'est une machine assez compliquée parce que ça devait faire du calcul scientifique aussi, des entrées-sorties avec des capteurs. Donc, pour lui, je pense que ça a été un plaisir de faire ça avec un hyperviseur, donc un multisystème microprogrammé. Hein. Et tout ça, donc, jusqu'où là, il est parti de sa théorie pour faire le géoprocesseur. Je pense qu'il a dû faire un peu une synthèse entre les deux, faire un peu de top-down, bottom-up. Et alors, ce qui est intéressant, donc, à la fois faire une grande théorie, prouver que ça marchait, que ça collait à la réalité, prouver que c'était utile, mais avec toujours beaucoup de pragmatisme. C'est-à-dire qu'à un moment donné, dans sa thèse, il dit ouais, ben, si une théorie ne sort que des résultats triviaux, c'est pas grave, ça veut dire qu'elle marche. Donc, si une théorie retrouve ce que j'en sais déjà, c'est pas grave, en gros, il disait. Oui, et un autre point, c'est qu'à ce propos, l'innovation radicale, l'innovation pour l'innovation, il n'aimait pas trop ça. Je me souviens, chez Bull, il disait souvent, mais chaque fois qu'on innove, on perd d'argent. Ce qui vaut mieux, c'est faire des choses de bonne qualité, de très grande qualité. Il ne faut pas faire mieux que les voisins en termes d'innovation, il faut faire mieux en termes de qualité. C'était quelque chose qu'il répétait souvent. Alors, si on regarde un peu, voilà des extraits de sa thèse. Donc, et bien là, c'est les choses de base, c'est-à-dire qu'il avait une longue définition, il a formalisé ce qu'il appelait un e-processus, et puis tout système était une hiérarchie qui pouvait être assez sophistiquée, de couches de processeurs et de ressources. La grande idée, c'est que si on coupe un système à un certain niveau, disons, ben, on peut considérer qu'en dessous de ce niveau, c'est un processeur, et au-dessus, c'est un programme à exécuter, pour simplifier. Donc, ils généralisaient la notion d'interprétation à tous les étages. Et alors, là c'est ces dessins. Et là, par exemple, visiblement, dans sa tête d'état, il disait, il faut que je mette un peu de théorie dans les coins. Donc là, il faisait des travaux sur les graphes. Là, il s'inspirait un peu, ça c'est une notation très kunzmannienne, sur représenter tout ça comme des treillis avec des choses compliquées, d'intersection de treillis, ou d'union, ou de séparation des différents niveaux. Alors, voilà, alors des fois, ça conduisait à des choses assez compliquées. Bon, un grand problème, tout le monde s'intéressait à l'époque, c'était la synchronisation des processus. Hein, les Dijkstra, les P, les V, les forks, les joins, bon, alors maintenant, les threads ont simplifié tout ça. La notion de tâche, de processus, on n'en parle quasiment plus, de manière bizarre. Et donc, lui, voulait faire ça très sérieusement. Alors, quand vous aviez plusieurs processeurs qui partageaient une mémoire avec des processus sur des machines virtuelles et ainsi de suite, bon, il arrivait à formaliser tout ça avec sa propre notation et ses vocabulaires. Ici, je ne sais pas si vous voyez bien, mais ce sont des articulations qui exécutent des inductions. Vous voyez, ce n'est pas un langage habituel pour décrire les machines, mais c'est ce à quoi il aboutissait. Alors, voilà, justement, à propos du géoprocesseur, donc voilà le vrai, sur votre gauche, le géoprocesseur au niveau physique, et puis le géoprocesseur vu virtuellement à travers ces couches architecturales. Et pendant ce temps-là aussi, donc il a fait ça, il a publié sa thèse en 1974, et donc c'était le moment, je pense, où il commençait à faire son rétro-engineering incroyable des processeurs avec un microscope. Puis en prenant des photos avec son microscope et en collant les photos sur le couloir, sur 20 mètres de long. Donc à la fois, il était dans le cambouis qu'il adorait, et puis en même temps, il était en train de sortir cette œuvre assez abstraite. Alors, quelque chose que l'on peut dire, c'est que cette théorie-là, en fait, évidemment, est une théorie très générale de système en couches. Chaque niveau est une ressource pour le niveau suivant, ou précédent. Et donc, ça peut servir pour d'autres choses. Hein. Cette chose-là pourrait très bien servir pour décrire des organisations, voilà, je pense des architectures physiques, tout un de choses. Et on peut se dire peut-être reprendre ces idées-là, ça pourrait être utile un peu pour concevoir, architecturer les applications que l'on doit faire aujourd'hui dans un monde virtuel avec des ressources plus ou moins infinies, mais avec des couches logicielles qui s'empilent, et ça pourrait être très, très utile. Un autre point important, c'est qu'il utilisait beaucoup ça en pédagogie, pour expliquer ce que c'était un ordinateur. Vous savez qu'il avait des talents de pédagogue extraordinaires. Quand il était devant un dessin de Pentium, là, il était ailleurs, quoi. Il était au paradis. C'était fabuleux, autant parfois, comme on l'a dit, il était un peu rugueux dans la vie de tous les jours. Quand il était sur scène, là, c'était un plaisir, et pour lui et pour nous. Alors, je pense cette idée aussi d'essayer de concevoir une théorie unificatrice, c'était un moyen pour lui peut-être de se rassurer. Il voulait toujours plus, toujours inquiet, toujours insatisfait. Peut-être pour lui c'était une démarche intellectuelle très, très profonde. Alors cette démarche, il a même été plus loin, parce que je ne sais pas si vous savez, il a publié un livre également qui s'appelle « Vers une étude objective de la conscience ». Donc le monde du hardware ne lui suffisait pas, il fallait aussi voir comment marchait le cerveau, et là-dedans il parle aussi un peu bien sûr de systèmes hiérarchisés. Et pour conclure, il met une citation dans chacun de ces chapitres là, et la dernière citation est très belle. Félix qui poetut rerum cognoscere causas, ce qu'il a traduit par « heureux celui qui a pu pénétrer les causes secrètes des choses ». Je pense que c'est tout, François, et je crois, comme disait, pour paraphraser Camus, il faut imaginer François heureux. Je vais juste, si le micro me permet de faire une petite annonce. Le 30 novembre, dans le cadre de l'Institut Frédéric Buhl, que je préside maintenant et dont il était un des membres actifs, animateurs, le 30 novembre, au Musée des Arts et Métiers, il y aura une journée d'hommage à François Anceau, Alice Rogoc, Alain Colmer-Roher, inventeur de prologue, sorti de l'ENSIMAG en 1963, il y en a qui ont dû le connaître ici, qui pourraient en parler, et puis Michel Hugon, donc, qui a été évoqué. Donc ça sera le 30 novembre au Musée des Arts et Métiers.
Merci beaucoup.